All right, so this is chapter 4, Think and Explain. Problem number 58. You exert a force on a ball when you toss it upwards. How long does that force last after you leave the ball? Now, depending on how you're holding onto the ball, the force could be either friction force or normal force or some combination thereof. But the big thing is that both of them require a contact. And so once the contact is gone, those forces disappear. So the force lasts as long as until it leaves my hand, at which point it's all force due to gravity. Now, the force due to gravity is still acting on it while it's still in your hand. That's why you feel some weight in it, although actually you're feeling the normal force from the ball onto your hand. And so there is that weight will still be there. And so once it leaves your hand, that's the only force acting on it. And so it's now a projectile motion. I am making the assumption that I have no Jedi powers. At least that's the claim I'm still going with. And so once it leaves my hand, I have no power to influence it. 62. Which contains more apples? A pound bag of apples on Earth or a pound bag of apples on the moon? Now, I am assuming that he's talking about that there's a pound of apples, not that the bag is a pound. And so weight depends upon where you are. It is easier to have a pound on Earth than it is to have a pound on the moon. And so therefore it requires more apples on the moon in order to balance that out. So the second part is about the kilogram bag of apples, kilogram bag of apples on the moon and on Earth. Mass doesn't care about where you are, so if it's a kilogram both places, it's going to be the same number of apples. 64. In orbiting a space vehicle, you're handed two identical boxes, one filled with sand, the other filled with feathers. How can you determine which is which without opening the boxes? Now, you can put them on a scale, but that won't tell you anything. And we did a demonstration in class where we put a 2 kilogram mass on a scale and we dropped it. And when we dropped it, it no longer measured the weight of the object because scales actually measure normal force. And so if they're both in free fall, that they're not exerting a force on each other. So in the case of an orbiting space station, you actually are in free fall in orbiting space station, and we get that in a couple of chapters where we talk about that. And I think it's chapter 10 officially, but I might bring it up earlier in chapter 8. So you're simply in free fall, but you keep missing the Earth. And so since you're in free fall, the scale's going to read 0. So you have to go to the other type of measurement on it, as we just apply a force to it, and we check the acceleration. So if I apply the same force on both objects, then the one with less mass is going to accelerate more and will go faster. So presumably the box of feathers. Number 65. Empty hand is not hurt when it bangs lightly against a wall. Why does it hurt if you're carrying a heavy load? Which of Newton's laws is most applicable here? So if my empty hand hits a wall, then I basically have this amount of mass that is trying to keep it going. So it bangs into a wall, and that's it. The mass is little, so for whatever the force that the wall applies to it, there's enough acceleration that it'll bounce it off. If I have a massive load in my hand, then suddenly it's not just my hand going into the wall, it's my hand and then whatever's in my hand. And so that entire mass, very similar to the principle of wearing a seatbelt in a car, which basically makes your mass part of the car. So if the car stops suddenly, it's the entire mass that has to stop, as opposed to just you. Now, if you're not wearing a seatbelt and you hit the brakes real fast, and hard, then suddenly nothing's holding you back. You're not really part of the car. You're a separate object, and then you will just fly forward, Newton's first law, and you won't stop until you actually hit something hard, like steering wheel, windshield, or something equally as deadly. And so if you're carrying a heavy load, the force that's being applied to your hand, even if it's the same force, there's much more mass, and so there's less acceleration. It's harder for your hand to basically change velocity. Number 70. What happens to your weight reading on a scale you stand on when you toss a heavy object upwards? All right, if you think about the force diagram of box on ground or man on scale on ground, if I throw an object upwards, that means I have to apply an upward force to it. if I apply an upward force to it, that means it applies a downward force on me. That extra downward force means that I need an additional normal force from the scale acting up. Now, since the scale is now not only supporting me and supporting the ball that I just threw up, or the force of the ball I just threw up, the force on the ball I just threw, tossed upwards, then that means that I'm exerting a greater normal force on the scale, and therefore the scale should measure a higher number. 72, mass in kilograms, my weight in newtons. I weigh about 220 pounds here locally, or 215 pounds. I think I'm down to 215 or up to 215, depending upon which point you tuned in. I can convert that into newtons by just taking that 215 pounds and multiplying by, 4.448 newtons per pound. The pounds will cancel out, so it's basically 215 times 4.448, which puts it somewhere around 1,000 newtons-ish. Then I can, to get my mass, I would, since my weight is equal to mg, I divide by g and I get my mass. So I take about roughly 1,000 newtons, divide by 9.8 meters per second squared, and I get really roughly about 100 kilogram mass. So my mass is about 100 kilograms, my weight's about 1,000 newtons. That's number 75. Explain how Newton's first law of motion can be considered to be a consequence of Newton's second law of motion. All right, Newton's second law, F equals ma. If the total force is 0, then the acceleration is 0. If acceleration is 0, that means my velocity doesn't change. So an object in motion will tend to stay in motion at that speed and direction unless acted upon by an outside force. If at rest, well, that's still a velocity of 0. Will stay a velocity of 0. And so Newton's first law of motion really is just basically saying that an object has no acceleration unless there's a net outside non-zero force acting on it. Number 77. An auto in the sketch moves forwards as the brakes are applied. A bystander says that the interval of braking, during the interval of braking, the auto's velocity and acceleration are in opposite directions. Do you agree or disagree? I agree that when velocity and acceleration are opposite directions, that objects slow down. And so that's the essence of it. It really doesn't matter. So again, there are a number of people that I've seen on the lab and other places which still associate negative acceleration with decelerating, positive acceleration with speeding up. That is just not the case. It all depends on what you consider the direction. It's more important to consider if the acceleration and velocity are in opposite directions, an object will slow down. If this is velocity and this is acceleration, well, if acceleration is in that direction, that means there's a force in that direction, a net force. So imagine you're going this way and someone pushes you in the opposite direction. You will slow down. Number 89. A parachutist, after opening her parachute, finds herself gently floating downwards, no longer gaining speed. So that's terminal velocity. I'm not sure that floating is really the right word there, but she feels an upward pull of the harness while, and he says gravity, he should write the force of gravity, pulls her down. Which of the two forces is greater? Are they equal in magnitude? So if she is not gaining speed and she is floating down, so she's not sort of going side to side, if she's floating down at a constant speed, that means that the forces are in equilibrium. The total force up equals the total force down, so the magnitudes are the same. The forces aren't equal because they're in opposite directions, but the magnitude is the same. And that's it for the Think and Explain.